Here's the field between oppositely charged parallel conducting plates. When two plane parallel conducting plates having size and spacing shown above are given equal and opposite charges, the field between and around them is as shown in A. Most of the charges accumulate at the opposite faces, so you can see that most of the charges here are accumulating here where this field is quite strong, and very few are accumulating on the outside. And the field is nearly uniform in the space between, so you can see as we're looking down here, if these plates are very long, you can see we've almost got a uniform field. You know, there's only a slight bending on the edges here, yeah, but in between it's pretty uniform. You know, in other words, they're all parallel field lines. A small quantity of charge resides on the outer surface of the plates, and some spreading or fringing on the field occurs at the edges of the plates, which I've just said. As the plates are made larger and the distance between them smaller, the fringing becomes relatively less. Often the fringing is entirely negligible. We will usually assume that the field between two oppositely charged plates is uniform. So we're going to assume that these are all parallel field lines, as in B. So now we're going to make this assumption that there's no outer charges, and all the charges are distributed between the two plates on the surface as shown here. The electric field at any point can be considered as a resultant of that due to two sheets of opposite charge. Thus at points A and C in diagram, the components, in other words electric field 1 and electric field 2, are each of magnitude the charge density divided by 2 epsilon naught here, that each of those are equal to that, but are oppositely directed, so the resultant is 0. So here you can see that there's going to be no field contribution at A or C, because they just cancel. At any point B between the plates, the components are in the same direction, and their resultant is, so here you can see any point here, the field lines are going to all point in the same direction. So we end up with E equals the charge density over epsilon naught. Basically, because the E1 and E2 are adding together, the half coefficient, if you like, simply turns to 1 because there's two of them, yeah? So we end up with E equals the charge density over epsilon naught.